One, two, three, one, two, three. Okay, our dear friends, we are ready to start our next lecture. And head of research group in Applied AI Center in Skoltech, Egor Shvetsov, would like to tell you much more about efficient machine learning training. So please welcome Egor.
So hello guys. So projects, right? How's going? Right now? Okay, cool. Any progress with projects or any troubles, any problems, anything? Only problems. But when you solve problems, you kind of progress, right? And you achieve something. So problems are good. If you have no problems, like kind of there's no progress, nothing to solve. So problems are actually good. Cool, cool. Okay, let's talk briefly about efficiency. What I want to talk about today, it's a new topic. It's a new topic for me. Guys, if you're deeply in the projects, right? I don't mind. I don't mind. Focus on the projects. When you kind of scatter your attention on several things, bad things happens. It's better to focus on one thing, to be more precise. Yeah. The topic I want to discuss today is relatively new for me, for myself. Usually I talk about specification, efficient models, model compression, and stuff like that. Today I want to talk more about efficient model training, how to train models faster, because it's a more interesting direction. It has been researched, it hasn't been researched that much as efficient model inference. So the question for you, what could be the difference between optimizing model inference as we have it versus optimizing models training? Yeah, the question, guys. So usually we want our models to be fast, right? To be computationally efficient, to kind of consume not so much memory. And we name it, we call it computational efficiency. We call it computationally efficient models. But sometimes we want to have computationally efficient training of our models. So what would be the difference, in your opinion, between optimizing model inference versus optimizing models training? Yeah. Yeah, exactly. So the main difference, we need to optimize the backward. This is the main difference. Cool. Okay, guys, we will talk about such stuff like matrix multiplication. Let's say we have two matrices here. Sizes are given here, like NP, P by M, like, again, N by P and P by M. And we have our result. I asked this question many times, like most of my talks. If you've seen it previously, you know the answer. But if you haven't seen it previously, you don't know the answer. And what I want to ask you, how many operations of multiplications and additions would this operation consume? So when we multiply matrices, we have operations of multiplication and operations of additions, right? And we call them flops, floating point operations. And we can estimate our computational efficiency in terms of flops, floating point operations, so-called floating point operations. So if you multiply two matrices of such size, how many flops will it consume? Yeah. Okay, yeah, true. And by two, right? Yeah, by two. So the idea is we will have N by P. Yeah, this answer actually. Okay, no. So we will have two NPM. We will have two NPM because we have NPM additions and NPM multiplications. And because we have both additions and multiplications, it's a naive way to compute it if you have kind of naive approach to do it. Also, in terms of computational efficiency, we have memory, we have latency, and we have energy. So guys, who knows the difference between CPUs and GPUs? Okay, okay, 2 hands, 1 hand, 2 hands, okay, several hands. So what's the difference? Oh yeah, where are hands? Okay, yeah. Processing units. Okay. The question for you, what's the difference between Ascent NPU and GPU? No, it's a tricky one, sorry. Sorry? Okay, cool, awesome. I mean, if it's in the process, awesome. So basically, CPUs perform smaller operations, but very fast. So it changes, it's like a racing car. It changes its direction very fast, very quickly. And GPU it's like, uh-huh. Okay. So GPUs are like huge track. You load it with a lot of tensors, and it carries it somewhere in your direction, in some direction. But it doesn't change direction very quickly because you load GPU with a lot of tensors, and that's it. That's the main difference. That's the main difference between CPUs and GPUs. So that's why they perform differently. For example, when you have many separate small tasks, CPUs are preferred, and when you have, let's say, homogeneous task like tensor multiplication, GPUs would perform better because you load GPUs with some homogeneous task, and they will work much better. Another interesting thing that when we talk about latency, we have two criteria. It's so-called memory bound and compute bound. And this happens due to a construction of our GPUs and CPUs. We have L2 cache, L2 cache, L2 cache here, right, and L3 cache. And DRAM, this is a unit of memory, which is, you all know, like you say, okay, I use NVIDIA 800, right? And it has 40 gigabyte of memory. So usually we talk about this DRAM, this 40 gigabyte of memory. The thing is, when we start computing on GPUs or CPUs, we take our tensor and move it to L2 cache first, and then we move it to tensor cores to perform some multiplication or something. And this procedure, right, from like moving our tensors from one memory to another memory, it's time consuming because you're actually physically doing something, like transferring something. And it's called memory bound. So memory bound is when your computation time is limited by how fast you move your pieces of information on your hardware. That's memory bound. And as we can see here, like if increase batch size, memory bound is increasing. Like our computational speed, let's say a number of tokens per second is kind of like, yeah, it's increasing. So we become kind of slower and slower here. What is compute bound? Compute bound is here in this part because we cannot compute more than we have. Like we have some number of tensor cores here, right? And we cannot place like more tensors in this unit. This unit cannot compute faster than it can. So it's called compute bound. The question for you guys, modern LLMs, are they memory bound or compute bound? We talk about inference now. Yeah. Why? So you're right. They are memory bound. And the reason is quite simple because model weights are huge. We will spend just a lot of time moving model weights into the GPU. we are not talking about activations. We're not talking about tokens and anything else. We are talking about model weights themselves, moving like from this part of memory to here. That would take a lot of time. Cool. And another category of models efficiency, it's energy. We also need to care about energy because often we spend a lot of energy. Energy is especially interesting and important part of computational efficiency when we talk about edge devices like mobile phones and so on and so on. Even for relatively big models, like to train some large language model, we would spend a lot of money purely on energy, just to buy electricity. You probably heard the story that Bill Gates bought a nuclear plant just to support his research in training AI models. Yes, things are connected. So, how to make models faster? I mean, that's simple, right? We reduce memory, we reduce flops, and make operations faster. Your ideas, how can we reduce memory? Yeah, it's simple, right? It's obvious question, just reduce the memory. So, but how? Pruning, okay, what else? Quantization. Why quantization helps? Yeah, yeah, exactly. Quantization helps because we use like 16 bits, then use 8 bits, yes? Structured represent, okay, cool. We will get back to it. Some other ideas? Pruning, yeah, pruning, why not? Okay, how can we make operations faster? I mean, okay, memory, okay, flops, and understandable. How can we make operations faster? Parallelize them, okay. What else? Caching, cool, that works. Yep. So here you actually talk about reduced number of floating point operations. Yeah, but then we want to make the same operations but faster. Yep. Build much powerful processing, but if you don't want to consume more energy, guys, like we always can accelerate things by throwing much more power, much more resources at it. But if you don't want to throw much more resources, if you want to preserve our energy, so what are options? You know it, you know it. You've heard it, yes? Less memory consuming data types. Yeah, that works. It works, but yeah. Yeah, exactly. Yeah, also works. So basically what you just said, we need to perform some sort of optimization to make them faster. We know this word, just optimize. Like the thing guys done with flash attention, right? They performed an optimization. They just look at the algorithm, how it works, and they performed an optimization. And we're able to perform some optimizations. So about the methods. Guys, like I have here specification and quantization. And again, you can look at the slide, you can use your own memory, your own cache, whatever. Um, how specification and quantization make operations faster? Yep. Okay. Yeah, cool. And in case of specification, yeah, that's exactly. You look at the slides, right? Yeah, okay. Okay, cool. Yeah, that's exactly here. So in terms of sparsification, we would have fewer computations. They will kind of reduce these ones to zero and try to skip them. In terms of quantization, we will kind of change our data type from FP16 to integer 8, and it will increase our multiplication, because integer 8 multiplication between two integers would work faster, just because it uses less hardware resources. So the good thing about sparsification, it preserves floating point range, because floating point range is here, it preserves it. And the good thing about quantization, actually, in the reality, it kind of provides better approximation for the entire tensor, for the entire matrix. So again, question for you. If we use matrix like this, for example, we use our PyTorch, we zeroed out a lot of weights. Let's say we use magnitude pruning, magnitude like thresholding. We take weights with the smallest magnitude, like the cases here, 1.4, 1.1, and we zero them out. Would it increase our computation? Just we take our PyTorch tensors as it is and zero out some of the weights. No, right? So why no? Because when we will perform our computation, PyTorch will count this as floating point operations, and these operations will be still performed, even though let's kind of imagine and try to come up with some algorithm which will allow us to perform faster operations here. We will need to keep the index of all zero elements to skip them during computation, right? So, and what happens actually, to increase to use the sparsity pattern to increase our efficiency, we need to come up with more constructions, with more operations. So we need to have some index to store where zero elements are located in order to skip them during computation. So and this is a very tricky part, because on one side, yes, we have fewer computations, but to enable them, we need to have more computations. Unfortunately, it's not that kind of simple. And with integers, exactly the same story goes for integers, except integer data types, they're more common on hardware, on nowadays hardware, and it's easier to enable kind of some gains when you use integer data types compared to sparsity. And also we have some architecture-specific tasks. I moved them here because in architecture-specific tasks, like, flash attention, it increases, kind of enhances efficiency of large language models. But it doesn't enhance efficiency of some, let's say, ResNets. It's an architecture-specific solution. And we have many architecture-specific solutions. This is like not a general solution. It's a solution for a specific problem. And usually, surprise, surprise, this architecture-specific solution, some heuristics, they provide much more gains, much more efficiency, because we know the problem, we know how to optimize it, and usually gains are much better. So if we use different data types like int8 and fp8 data types, and these are like, here we have accuracy or error approximating different distributions. And here we have integer data type with exponenta 2 mantissa 5, exponenta 3 mantissa how much mantissa 4, and so on. So guys, who knows like exponenta, mantissa, all this stuff? Okay, cool. So what is it? So what exponent is responsible for?
exponent is responsible for number of positions that we move our point.
Yeah, okay. So in other words, exponent is responsible for the range of values, for the range of the possible values, and mantissa is responsible for the precision. And what we have here? We have here that, look, if you have integer data time and uniform distribution, integer approximates it quite well. If we have like normal distribution, integer approximates it quite well, but floating point data type, exponent 2, and precision 5 here, yeah, mantissa 5 here, it would be better. And we have data type with heavier tails. With heavier tails, integer data type doesn't work well, and we need bigger exponenta like E4 here. Because we have these tails, we have this range of values. So we would need this bigger exponenta, but overall performance drops because precision is lower here. So guys, this is a data format. It's called 2 by 4. Who heard about this data format, data type? Okay. Nobody, right? Or somebody heard about it. Okay, so what is it?
It's a format when you just have to, in each 4 bits, move, like set 2 bits to 0. So you can just perform less operations on this part. So you have chunks and you have to sparse some of them. So yeah, it's an architectural support for that.
Yeah, that's totally true. Look, so we have, let's say we have some sub rows by 4. That's why the format is called 2 by 4. They have the total length 4. And with the total length 4, within this sub row of 4, we will zero out some 2 elements. And we will keep indices of these elements in another matrix, in the matrix here. Then in another subrow, we zero out this element and this element, and we will keep indices here in another matrix. Therefore, we will have like dense matrix here with all dense values, and we will store indices of all 0 values here. It's like a colleague said, we need some pattern, we need some structure. The question for you, why do we need 2 bits to store these indices? Yep.
Because we removed the zeros and we need to know where it was after the operations, where will be the activations which is not non-zeros.
Yeah, because the total number is 4, right? We just need 2 bits. Yeah, I know you know the answer. I just want to talk. So that's it. Another approach. So this is implemented in the current hardware. It's supported by most of the current NVIDIA GPUs. And on average, this approach allows us up to 2 times acceleration, but only when only when size of matrices is relatively big, because we still have some overhead of packing and unpacking these indices with 0. It's still an overhead. It's like I said, if you want sparsity, it doesn't work like that. We need to have more operations in order to have the sparsity work for us. And we will need to store these 0 indices here. Actually, 2 by 4 sparsity is not only like the only pattern. We also may have 8 by 16 sparsity. And if you look here, 2 by 4 sparsity requires like 0.75 bits per element, and 8 by 16 requires 0.875 bits per element. But it has much more configurations. It has way more freedom. Yeah, so it's kind of, bless you, it's kind of less efficient in terms of bits per element, but it's way more flexible. It's not supported yet. It's not supported yet in any current GPUs, but some companies work on this pattern, and it will be implemented quite soon. So this is something what will be in release maybe in a year or in a 2. Yep.
You said that this is a format of sparsity, but you select the elements that you want to cancel by yourself. How does it work? Maybe
okay.
you can cancel something useful.
Okay. So of course, we will cancel something useful. I mean, of course, there is some degradation when we use such approaches. It happens. Usually, how it works, you take this matrix, it's a dense matrix, and you remove values with the smallest magnitude here within this row. This is a very straightforward and naive approach.
Okay, thank you.
But then some actual work happens after it, because removing by magnitude is kind of straightforward. But so it may happen. I'll discuss this briefly, but it may happen. For example, this weight may have a small magnitude, but it may happen that on average, this way interacts with activations which has big magnitude. It may happen. And here some work happens. So we start to come up with some more interesting measures to understand if we need to prune this guy with small magnitude or this guy with big magnitude. And actually, it's a work in progress. It's a part of research right now. So this is a good question. And also, there are some approaches to reduce an error. For example, we can fine-tune the weight, right? But if the model is too big, we can perform different approaches, like without resorting to fine-tuning. And one of the efficient and kind of, let's say, obvious solution is to perform variance correction, because variance of this matrix will be changed, right? And we can, like, channel-wise perform variance correction. It will improve our performance, like simple like that, but it will improve. And so many tricks and different approaches are possible here to improve the performance. So initially, right, most of the models were trained on FP64, then we moved to FP32, FP16. Right now, most of the models support 8-bit training and 8-bit inference. Some of the models support FP8 training and inference. And as you know, DeepSeek, right, it was trained in FP8 to optimize training resources and memory. Some of the cards, some of the hardware supports 4-bit. Not so many cards support FP4. As I understand, only NVIDIA Blackwell right now supports FP4. And 1-bit is kind of CPUs and FPGA only. There are some new data formats are coming, which will be supported by new generations of GPUs. Like one of the format described in this paper, it's called microscaling, and it's specifically optimized for quantization. And another format, it's called Ascent High Float 8. It's obviously from guys who developed Ascent hardware, and obviously it will be implemented in Ascent hardware in some future. Basically, High Float 8, it's full precision floating point format with 8 bits, but Mantissa and Exponenta can be relocated on demand. So amount of bits between Mantissa and Exponenta can be moved on demand based on the task. So it's more flexible data type. So guys, I just said that we can compress and reduce, like remove some of the weight, right? We can quantize some of the weights, and when we quantize weights, we basically reduce the representative power. But the question is why it's possible. Yep. Good question, but why do we have so many parameters? Okay, but why, how do we know? Empirically, okay, cool. So let's think a little bit. Why our models are over-parameterized? Yep. Bigger models converge faster. Cool, I agree. Yep, you're right.
heard that there's a phenomenon called double descent. Then when the number of parameters grow, then first of all, the mistake may decreases, then it increases, which is called overfitting, and then it starts to decrease again, which is double descent, and this is the pattern which we typically observe in neural nets, and that's why they work in some specific interpolation mode, and that's why the number of parameters these models have is
Yeah,
too
totally
much.
agree. Totally agree. Yes, some idea was here, right, in this direction. Okay. Yep. Was there?
Well, from my perspective, they are over parameterized because we know that the bigger the model, the more complex tasks it can do. Because the data, it remembers more data, it remembers more some intrinsic, I don't know, relations in data. So it's just a basic understanding of how neural network works. The better, the more it can consume data, and that's it.
Great answer. We will just in a few slides, in a few following slides, I will talk about like scaling laws and try to connect the data sizes. We will talk about connection of data size, number of parameters, and so on and so on. So you're guys right. It all depends on the data. It all depends on the number of parameters that models. I know you know. Yeah. Anyway. Yeah. Okay. It all depends on number of parameters. It's true that bigger models converge faster, but it's also one like let's say human-related thing. Let's call it human-related thing. It's obvious, right, that for different tasks, for different problems, for different data sets, we would need different models, different number of parameters, and different architectures. Are you kind of agree with me? Okay, so, but in reality, for all of the problems, we take some kind of pre-established models. We don't develop extensively new models for specific data sets, for specific problems, and so on and so on. We take some predetermined models, like we need to obtain embeddings. Okay, we will take some BERT model. It can be medical BERT, it can be like some other BERTs, maybe like there are 20 types of BERTs, but just 20, but a number of possible problems and a number of possible data sets is much bigger. So usually we take a model which is already over-parameterized. Because we take a model, it doesn't work on our data set. What we do? We take a bigger model and try to train it. Now it's also a human thing. So actually we could perform like a extensive neural architecture search or something to find the most accurate, most specific architecture for a specific data set. We don't do it because we need to obtain results faster. We just take a bigger model, train it, and it will lead us where it leads us. We have much more parameters. Okay, cool. Also, as you said, it all depends on initialization, training, optimization, dynamic, and data sets and data quality, of course. And about scaling laws. Like, I guess you're aware of this paper, like chinchilla laws or scaling laws. What has been done or performed in this paper, guys took different models, many actually models, with different number of parameters. And they trained these models on different number of tokens. Then they said, okay, connection between number of parameters, data size, and representation. Here, just imagine here is one. For now, this term doesn't exist. It's purely one here. So right now we discuss a connection between number of parameters and number of data points. And they said it would have such dependence, such yeah, it will depend on such equation, and we will try to come up with this parameters empirically. So we have many data points, our observations, and we will try to fit this dependency and obtain these coefficients. When they obtained these coefficients, they said, okay, actually the optimal number of parameters is as following. They did it, they trained the model, and they obtained better quality. So basically what they figure out a better relation between the number of data points and the number of parameters. And it's right now it's obvious. Right now it's obvious, it's important. I mean, data set complexity and size matters, and the number of parameters also matters. These things are connected. The next work which was performed, they did exactly the same, but actually they, so I'll move back actually. Okay, one more. No. Yeah, any questions here? Okay, how are projects going? Okay, good. No, if they're going, I'm happy. Actually, after the lecture, we can discuss projects and all project-related stuff. Yeah, look, this A, C, and E, and small d are parameters, and N and D, number of tokens, number of parameters, data size. This is a data size. Here, just one. Here, just put one. In this, it will be important for the next slide. Here, just one. Just skip this stuff. And yeah, Alice loss. So and we search for such. So we empirically train many models, and we have many empirical observations, and then we try to fit this model to find the dependency between number of data points and model size. That's it. So what has been performed later, actually, this parameter happens. Right now, we plug in this parameter. It's like a multiplier to the number of parameters. This multiplier for the number of parameters, it's some coefficient which is responsible for data type representation, whether it's quantization, whether it's sparsification. And if we see, so they performed exactly the same thing. They just trained much models because there are way much more configurations, because we can have 8-bit, 4-bit, 2-bit, and 1-bit, and so on, and various types of sparsity. What we can see here, that 8-bit representation, it's almost the same as 50% sparsity. Which is kind of cool, which is interesting. But if you scale it further, 4-bit kind of scale, I mean, if we use 4-bit, it degrades number of parameters like 0.7, right? But if we have 75% sparsity, it degrades much faster. So on average, we see that 4-bit is kind of more optimal solution, because 4-bit would provide more efficiency in terms of computational cost, in terms of number of bits per parameter, and so on and so on. So like using this empirical observation, we can see that it's more efficient. 1-bit doesn't work at all, and 2-bit also doesn't work well. One note on this research, on this paper, so to perform this work, this team, they didn't evaluate, let's say, most efficient quantization methods. And they didn't perform most efficient like 1-bit quantization methods or compression methods. They took something naive, some baselines. What it means that numbers here could be actually higher, in reality, but maybe not that much higher. Also, for the numbers here, they could be slightly higher, but also not much higher. Right now, we live in a situation that, this is kind of our optimal solution, and this is also our optimal solution. And it's an important note here. It's a really important note here that right now we talk about weights representation type. So we talk about weights, that weights are represented in 8 bits, and sparsity level of weights is 50%. The reason I highlight weights because we have gradients, we have activations, and so many things, right? So there are two compression paradigms. First, like train model first, compress after, and compress model and while training. And usually we apply quantization or specification, and sometimes we apply some architecture-specific heuristics like flash attention or anything else. So what's missing here? What is left? Yep.
Compressing the data.
Good point. We will talk about it later, just briefly. We want to increase training. The problem is here that we train, but nobody talked about increasing performance of training, increasing speed of training and training efficiency. And actually, that's the topic I want to talk today. So before it was kind of pre-topic. I don't know how to call it. And right now, the topic itself starts. This topic we started to focus on with our team relatively recently. And I'll share some of our results, and I'll share some of the results from the literature. As for any new topics or any, let's say, emerging topics, there is not much of information, or there's not much kind of proved concepts, and I will not kind of talk a lot. There is not much to talk about. Most of what I know, I'll share on the slides. Most of what we tested with our team, I'll share on the slides. And then I will present some kind of future directions and my thoughts on the topic. In other words, what I wanted to say, this topic is relatively new for myself as well, but it's interesting. How can we increase training efficiency? Actually, there are various directions like quantization, structured sparsity, dynamic sparsity, distributed training, algorithmic optimization, and actually data efficiency, as some of the colleagues said. In terms of data efficiency, it's true. We can clean our data sets, remove some noisy points, make some so-called core sets, which will help generalize our models much faster. Algorithmic optimization like KV caching, flash attention, page attention, and so on and so on. Most of these guys are for LLMs. Distributed training is good, but it requires more energy consumption, and it's not that interesting. You just throw more power at the same problem, and it's not fun to do. Dynamic sparsity is really interesting, and I'll talk about it later. Structured sparsity can be seen as a dynamic sparsity, and quantization, we just talked about it briefly. So, dynamic sparsity. What can we do with our activations during training? Let's say we have a small magnitude here and here, like here and here. This is some like, small magnitude here, and we have some thresholding function. And when we apply this threshold, before applying this thresholding function, we can recollect, reshape our tensor before multiplication, and we have profit. That's as simple as it is. Just don't waste our compute on something which is not really important here and here, and we will have a profit. And this is straightforward. It's not the kind of the most well-studied direction, but it's straightforward as it is. The question is why it's possible. I forgot I plugged this slide in. I was surprised. Yeah, I mean, the question is why some of the activations would be close or almost zeros. Yeah.
Yeah, well, but not all activations are equally important on all inputs. So
It may them sound is straight faster. You need both matrices to be integer types. Then it will be faster matrix multiplication. And again, even such simple operation is not free. It's cheap, but it's not free. So and the problem is if you have small matrices of a small size, these small operations will be significant. If you have matrices of a big size, these small operations will be insignificant. So this optimization procedure would actually work for big matrices. In other words, most of the methods which are directed on improving training efficiency would work in scenarios with big matrices, but will not work in scenarios with small matrices. Good thing, we need them for big matrices. We don't need them for small matrices. This is results from our common work for those knows about this work. And the main idea here that different sizes of matrices, different, let's say, types of tensors, they would accelerate differently, and sometimes they will not provide any acceleration. For example, here are given matrix sizes. And if matrix size is relatively big, and we have a relatively big batch size, we can accelerate by 27% using a quantization operation. If batch size is small and matrix size is relatively small, we will be slower. We will be much, much slower, actually. So we may obtain some significant gains in some scenarios, and in some scenarios, we will be much slower. But for example, almost 30% training acceleration for some large language model is a lot, right? Because it can be trained by months. And if we save a couple of, if we cut it in 30% or 2 times sometimes, that's quite a lot. That's significant. Okay. Yeah, it all depends on the budget and the size. Okay, yeah. And if we compare total model acceleration, this is presented here. They presented some transformer-based architecture with different sequence lengths, different batch sizes, and we applied semi-structured sparsity and quantization. We don't talk yet about quality performance. Right now, we talk only about possible gains, possible acceleration. And we can see that the structural sparsity provides us 1.5 acceleration, and integer 8 provides us almost 2 something acceleration. So integers actually seem to be more interesting in terms of accelerating forward-backward operations than structural sparsity. So guys, to accelerate model training, we can specify weights, specify activations, quantize weights and activations. And the spoilered, it was spoiled, the spoiler has been demonstrated. We also can work with gradients. The question for you, during training, our computation is dominated by forward path or backward path? What is more computationally demanding? What takes more computational? Backward path, of course, backward path, true. So it's almost twice more computationally demanding, backward path. And basically that's the place where we need to focus. And the good thing, many empirical papers demonstrate that backward path is gradients are sometimes sparse. And now we can employ some strategies to perform sparsification on gradients. Here's an idea also from our joint work with colleagues who are also here right now. And here we can see that if we perform gradient sparsification, we can accelerate almost 1.5 times, sometimes without any significant drop in performance. Why? Because gradients are quite sparse. That's it. We just remove some of the gradients and we can accelerate 1.5 times. That's almost for free. It's not true for all of the data sets. For example, data set here, or data set here. And again, that's the problem that some of the data sets are more, let's say, difficult. Some data sets are, let's say, easier, and it really depends on the data and model size. But it's a work in progress. It's a work in progress, and yeah, it's an interesting direction to look at. So can we do better? Can we do better than just specifying the gradients? What else can we do with the gradients? Yep. Fantastic. Yeah, I mean, yeah. Something else? Yep. Different optimizers. Yes, yep. Actually, it's also a good direction. We wanted to look into it, but we didn't have time because there are some, let's say, noise robust optimizers which are robust to noise. And it's really interesting to combine this noise robust optimizers with quantization, because quantization is actually, let's say, integer 8 quantization is equivalent, like you add to our weights Gaussian noise. It's very similar, and therefore like noise robust optimizers, it's an interesting direction to work with and to see. True, something simpler, like more engineering, I would say. I will show you. So, okay, now, yeah, here. For example, we want to quantize our gradients. We want to quantize gradients, right? We use this quantization thing. So what quantization is? Quantization is basically is a mapping of our of some range of values into some discrete range of values, and this discrete range of values, number of possible values, is predetermined. For example, for int like for 2-bit, we will have 4 possible values. For 3 bits, we will have 8 possible values, and so on and so on. So what may happen? What may go wrong here? If we want to quantize these guys, and we use this kind of abs max scaling.
The zero.
Yeah. So this is an error with 3 bits. There should be 8 possible values. I don't know why I drew 10, but the idea is this. For example, assume we have 3 bits and we have 8 possible values here. We split this range into equal 8 possible values because that's how uniform quantization works. And what we have one value here, right? And one value here. That's it. We lose all of the information. So how can we overcome this problem? Dynamic quantization. It wouldn't work because we will have this outlier anyway. So how do we deal with outliers? Projects. Yeah, it's a good thing you're working on them, I hope. So yeah, this is okay. The question is a problem like, I mean, this is a problem here? Yeah, okay, this is a problem. So the problem is that we have, let's say, 10 distinct values. And because we have 9 distinct values, we split our range into 9 distinct values uniformly, and they will collapse here, and we will lose all of the information. The reason why it happens, because we use this kind of EBS max quantization, right? Because we take max value. And yeah, what can do, we can compute percentiles and remove them. Any problems here?
Doesn't work?
No, it our goal is to increase training speed, training efficiency of our models. Let's say accelerate or improve memory efficiency and computing percentile. Quantization and specification during training cause computational overhead. So on one side, we can improve our speed by specifying or by quantizing, but quantization and specification, they're operations on their own. And because they're operations on their own, they also require some resources. It's possible to specify gradients. And most of the papers right now focus only on forward path quantization during training, interestingly. So if you look at the most of the papers, majority of the papers look at the forward path quantizations. When we talk about training acceleration using quantization, you will see that some of the methods, they quantize only forward paths, and they keep the backward paths and FP16, FP32 to preserve the accuracy. And one of the emerging directions is adaptive specification. When we train models and we specify activations adaptively, so models kind of train internally to work with sparse activations. It's another direction, and it's also kind of interesting and it's kind of emerging. So gradient quantization. It's a common technique in model quantization to apply Adamar transform, and Adamar transform will make our distribution more Gaussian-like. For example, we have a original distribution here. We apply Adamar transform, and our distribution becomes more Gaussian-like, and it's easier to quantize. Again, it's easier to quantize because fewer outliers here, as we just discussed. It's a good thing. It's simple, kind of straightforward. But again, guys, Adamar transform, it requires some computation cost. We need to perform the Adamar transform, and then we need to quantize, and so on and so on. So overall, this procedure would improve training efficiency because we quantize into integer 4. So from floating point 16, we move to integer 4, and on some hardware, integer 4 provides us enough acceleration to overcome this transformation with Adamar transform. But if we quantized, let's say, into integer 8, it could be not enough. So this operation could be too costly for us. Another really interesting approach, it's actually from an old 2020 paper, relatively old, but still. No, not this one. And I jumped. Okay. So I didn't put this slide for some reason. Okay, I'll explain it like this. So another approach from a paper to improve gradients is to use something similar to gradient accumulation, what we can do, we can, on the backward path, compute gradients only with magnitude, which is higher of some threshold. And other gradients, we can accumulate in some memory tensor, like a cache or memory tensor. And this would kind of cause no problems at all. So we will perform fewer backward operations using some threshold function, and we will accumulate our gradients in a separate tensor until it reaches like big enough magnitude. And then we perform backpropagation. And this is just for fun. It's actually 24 paper. It has almost nothing to do with training acceleration. It's just an interesting method I decided to demonstrate you. How people can compress models, just an alternative way to compress models, model weights. So it's just fun. What we can have, let's say we have some seed, right? And we generate a random matrix from the seed. We generate a random matrix from a seed. We have some like target tensor, weight block, and we have some coefficients. And let's kind of find coefficients and random seed. So after multiplying these columns to this, after basically multiplication on these coefficients, it will approximate this weight matrix pretty well. And people just start searching for these coefficients and seeds, and they find a pretty good approximation. Then to store matrix weights, we just need to store seed number and a small number of coefficients. That's it, profit. It works. It works. The problem with this approach is not that fast, but you can kind of quite compactly to represent your model with a small error. But is kind of the compression level will be quite big. That's just for fun. I mean, it doesn't have any, let's say, practical usability, as I think, but yeah, it's interesting. So, transformers. I'll talk briefly about faster transformers. how we can accelerate them because it's a hot topic. And I know I talked about some maybe not really exciting stuff. It's not going to happen again. I mean, I'm not going to talk about exciting stuff anyway, so nothing is going to change. So operations which dominate transformers. When we compute and perform forward path for transformers. We can see that attention starts to dominate when we increase input length. Some other operations and gem, it's a general matrix multiplication. Also, we have two stages for our LLMs, two stages which are called prefill and decoding. For familiar with these terms, prefill and decoding. Okay, I'll explain this two stages of prefill and decoding. They're quite simple. And you see how it works. So if our input length is relatively big, attention dominates. If input length is not really big, general matrix multiplication would dominate. It's on prefilling, and it's almost the same on decoding stage. The thing we discussed with you right now, how to accelerate general matrix multiplication, and it's this part. And we talked too much how to accelerate this part actually. Actually, we can also improve attention because attention mechanism contains much multiplications. It just this it's a different part. So during LLM, when we use it, we have two stages. The first stage is called prefill. The second stage is called decode. Actually, prefill stage, it's when LLM reads our prompt, entire sentence, and generating or decoding, it's a decode stage. During prefill stage, usually what we can do, we can cache our values, cache all our input, cache our input prompt, so we don't reuse it in the future. And the generation, when we generate, we use these cached values for the future. Nothing interesting actually and fancy here. What is common in LLM acceleration, improvement, we keep these Kiwi caches and sometimes we can remove some of the values. So Kiwi, these Kiwi caches, they would relate to some of the tokens and some of the tokens are less important than other tokens. And what we can do, we can remove some of the tokens. Just remove them and that's it. Also, we can remove tokens when we generate. We can kind of skip some of the not important tokens during generation. Also, we can merge tokens using some statistics. Let's say we measure cosine similarity. We find that two tokens are similar to each other. We weight them with some weighting similar or related to their cosine similarity, and that's it. And we have fewer tokens. If we have fewer tokens, we have much faster decoding operation. And another approach is sparse attention. We can sparsify our attention. And there are very, very different approaches to sparsify our attention. Like if you look into DeepSeek paper, they have some almost kind of ensemble of sparse attentions. And yeah, and it works too. A combination of such approaches when we want to compress or remove tokens actually leads to a big number of different papers recently. When people try to compress Kiwi caches, quantize Kiwi caches, sparse Kiwi caches, remove, and if you look into the Google Scholar, you'll see a lot of methods. But more or less, all of these methods are about the same thing. We want to optimize, remove some of the tokens. We want to optimize memory. We want to, when we quantize or compress our Kiwi caches, we reduce memory and we reduce this memory bound, which we discussed at the beginning, and therefore our model will work faster. So it's more or less about the same thing, just different approaches, and there are very many approaches to remove tokens. Another thing is that right now, yeah, the question for you, actually. As I said, there are many papers which demonstrate that we can remove some of the tokens from transformer. Like, for example, you provided some prompt and you removed some of the tokens from this prompt. Why it's possible? Guys, don't sleep. Work on projects, but don't sleep.
There is no attention on some tokens.
Yeah, okay, true. There is no attention on some of the tokens. They're kind of unimportant. What are other ideas?
Well, the same idea. Same idea. Some.
What's you? Yeah, okay, you can talk. So they don't carry any meaning, any contextual information. You hear?
I guess we can remove some tokens because, for instance, if a person reads, let's make analogy with a real person. For instance, if a person reads a text in a foreign language he or she generally understands and meets an unknown word, he doesn't see an unknown word, he or she doesn't pay attention to it, he just reconstructs its meaning. So I guess it's possible for a model to also reconstruct meaning from the rest of tokens.
Yeah, true. And also, you've probably seen some papers when people say that, look, we can compress a huge sentence or a paragraph into one token. Such papers exist. Also, your idea, like, for example, if a model trained on a really long context, it seems that attention will be more uniformly distributed. And it means from a bigger prompt, we can remove more tokens, right? I mean, probably yes. The question again, right now we have this token removal, token pruning strategy for LLM models. Is it going to work for diffusion language models? Nobody knows. We'll see. Yeah, you have an idea? No. No. Okay. So nobody knows. We'll see if such compression methods would work with diffusion language models, because they operate differently and they have different structure. Nobody knows. So this is a list of literature if you're interested in model training acceleration, and questions, and actually any questions, if you will. Also, we can discuss projects if you have enough time.
Thank you for the lecture. Can you go to the last slide about this tokens? You told about deleting some of the key cache pairs or doing other modifications, but so we do this to optimize the prefill stage, right?
Decode.
So after we have also made
because like during this part when we decode, we condition during decode we will here I'll show. Yeah, here we will condition on fewer tokens during decode, and decode will be faster.
Okay, and do we so we delete these tokens only from the prefill stage? So during decode we don't delete the generated one?
Yeah, during decode there are other strategies during decode, like speculative decoding and something like that. It's a different direction when you use a smaller model to generate some proposals, ideas, and then you use bigger model to validate. It's a different. Yeah, during decode we don't do it. So during prefill we remove some of the tokens. or we work with our attention metrics also to use fewer tokens.
Thank you for the lecture. And in the Mamba paper, they also introduced interesting idea of optimization for GPUs. They use embeddings of lower dimensions and pass them between two types of GPU memory, high bandwidth and static random access memory. And when they put it to a fast one, they increase the dimensionality project, this embedding, compute operations on this one, then lower the dimensionality and bring it back to the less fast.
Yeah, I see.
Maybe.
That's cool. It's cool. But the question is, in this paper, the question related to this paper, if the product in lower dimensionality leads to the same result as a product in higher dimensionality, why do you need to reduce it at all?
They actually say in the paper that it really improves the quality and speed up the operations.
No, I understand it improves the speed up because we reduce the dimensionality. The question is, why do we need to scale it up again?
They say like it helps.
Okay, it's interesting. That's interesting. Yep.
Yeah, thank you for your lecture. It was perfect. Can you please say a little bit about the future of the quantization? Because right now there is, the standard, I guess, rule of thumb is to not go beyond 4 or 3 bits of quantization, and it will be perfect if you use 8 bits of quantization. Of course, there is a quantized assurance training, etc., etc., but the quality of the model still drops pretty significantly after the 4 bits, I guess. So where will we, when will we maybe increase the quality of the quantization, still preserving the very small number of bits? Can you a little bit say about it?
So the current situation. DeepSeek paper demonstrated us that training with FP8 is possible. Actually, there were previous papers, but they trained much smaller models, and in DeepSeek just demonstrated that it's possible to train a really, really big model. Training models with lower precision, like integer data types, and FP8 data type, when you train a really large model, it takes months sometimes. And at some point, your model starts to diverge. And when precision is lower, when you use like low precision data types, probability of divergence is much higher. So people try to avoid it for a long time. Right now, I think training with like floating point 8 will become more popular. Post-quantization techniques right now are focused on 4-bit models because it's Pareto optimal. It's post-quantization techniques, I mean, when we train the models and quantize it, it's for large language models. Also, the thing is, for things I say, they mostly right now about large language models. Because if you talk vision models and this scaling laws for vision models, let's say for image classification, probably for image classification, 2 or 1 bits would work perfectly. Nobody kind of performed scaling law for image classification with lower bits because there is no need for it. Models are small enough and they work as good as they are. For lower dimensionality, I guess, I mean, for lower precision, we need to find better training strategies and to figure out if it's possible to train models with lower number of bits, like 1-bit models or so. And apart from it, representational power of lower precision, I don't think it was well studied, because with lower number of bits, we have lower representational power of our basically embeddings, representations, vectors, and it's also should be considered. So the answer is, I don't know. I know what should be studied. I know which directions are very important to look into, but I don't know the answer.
Thank you very much. And one more question. Am I right that it is better to train the model with quantization instead of quantizing the weights for inference, right?
Yeah, so if you quantize model during training, it would lead to better performance, but you have some probabilities that it will diverge. So that's the problem. Also, yeah, on average, if you use like 8 bits and train model in 8 bits, it would be much better than you train model if in FP32 or FP16 and then quantize it into 8 bits. That would be much better. But for example, if you want to talk about quantizing into 4 bits, and compare, like we are training model in 4 bits, and then we trained model, let's say in FP16 and quantized it in 4 bits. It's still questionable, because optimization procedure in int4 is quite noisy, and it doesn't guarantee that we reach some minima in int4 training. So that's the question here. It works, yeah, answering your question, it works for int8, it's true. For int4, for some models, yes, for some models, we need to see.
Okay, thank you.
Okay, guys, thank you for your attention. And if you have any further questions, I'm here. Further questions, and again, all project-related questions, all project-related kind of structure, planning, and all formal questions, you could address me. I'm still here. Thanks.